Okay, morning. As I sent you an email over the weekend stating that we were going to start casting the lecture live. So in case you cannot come to class, you can join via Zoom. That was a strategy that I was not aware of. So I was notified on Friday that we can offer that opportunity to the students as well. So if you choose to watch the video or watch the simulcast, that's also an option for the student. Just remember that the exams are going to be in class. So we have to be in class for the exams. So that's what we're doing. We're gonna simulcast, and then at the end of the, yes.
So, for example, if we have a lab at this day,
yes, so the lab will be available also online, so you'll be able to open the lab and work on it on at home as well. And you will understand more the dynamic of the lab today. The labs are not to penalize you, are more like a tool for me for open discussion in class. So I'll give you the one lab today. You're gonna work on it, and then we are going to discuss the lab in class, and you will submit that at the end of the day. So it's not that I will give you the lab, I will let you work on it, and if you get it wrong, then you have to submit that wrong answer. It's not like that. So you have another question or no? Okay, so on our last lecture, we stopped here. We were introducing the Gauss-Jordan method for solving a linear system of equations. And we went through this example, and then I asked you to review this and also to try to finish, because we went through the first two iterations or the first two columns for this solution. So hopefully you had a chance to work on it. And do you have any questions about how to get to that last final answer? So this is the answer. We get x1 equals 1, x2 equals 2, and x3 equals 3. And today we're going to start from here. We are going to learn how to differentiate the different type of solutions when you apply the Gauss-Jordan method. So for example, here we show this solution. We need to identify based on this matrix if this is a unique solution or if there's a multiple solutions, or if there are multiple solutions for this problem, or if the problem has no solution at all. So that's where we're going to start from, where we're going to start today. So I show you here two special cases after the application of the Gauss-Jordan method. A linear system having no solution or infinite number of solutions can be recognized. So in this case, we have a no solution example here and an infinite solutions example to your right, or the right of the screen. So how do you differentiate between these two types of solution? That's what we are going to explain now. Clicking. There we go. Okay, so first we need to understand the difference between basic variables and solutions to linear equation systems. So there's two groups of variables, or two different sets of variables that we need to understand. The set of basic variables and the set of non-basic variables. And obviously, if you identify one of them, then the other set will be the complement of the members of the other set. So for any linear system, a variable that appears with a coefficient of 1 in a single equation or in a single row, and a coefficient of 0 in all of the other equations or in the other rows, is called a basic variable. So if you have a column with 3 rows or a vector with 3 rows and you get a 1, 0, 0, that means that that column is representing a basic variable. Any variable that is not a basic variable is called a non-basic variable. So if it doesn't show that structure, that means that that variable or that column is representing a non-basic variable. Let the basic variables be the set of basic variables for this A prime X equals B prime system of equations, and the non-basic variable be the set of non-basic variables for that same system of linear equations. Then the character of the solutions for this system depends upon which of the following cases occur. So we're going to discuss 3 different cases now. Case number 1 is the case in which we are going to show that we have no solution. So again, we represent the system of linear equations as A prime X equals B prime. And then in this case, we have at least one row of the form 0, 0, 0, 0. So all zeros on the left side of the equation, and a coefficient that is different than 0 on the right side of the equation. So if you have something like that, like we are showing here in this last row, you have zeros on your left, and then the right-hand side of the equation is a coefficient different than 0, then that system, I mean, even if it happens only for one row, that system has no solution. Why is that? Because if you put that into an equation, you're saying that 0 is equal to 2. Okay, that's not possible. So that system has no solution. That's simple. So in the matrix, row 5 meets this case 1 criteria. Variables 1, x1, x2, and x3 are basic, while x4 is a non-basic variable. So again, we look at the structure of each column. We can identify the basic variables, a 1, and the rest of the column is zeros. So we have 3 variables, x1, x2, and x3. The other column has numbers that are not 0. So we can state that that column is representing a non-basic variable. So x4 in that case, remember that we named the columns based on the location of the precision variable. So that's why I'm saying this column is representing x1, x2, x3, and x4. So x4 is a non-basic variable. Questions? So yes. A free variable? What do you mean by free variable? It can assume any. Free variable and non-basic variables, they're so free means that you can assume any value, right? So it could be negative or positive, right? They are not in what we are trying to explain right now. I mean, in terms of defining those sets, they are not representing the same thing. Right now, what we are trying to differentiate in terms of the set is, are they part of the solution for this system of equations? So the basic variables are the ones that showing the actual solution for the system. In this case, an x4 is a value of 0 when you are inputting the solution into the system. A free variable can assume a value of 0. So that will be, I would say, an overlapping between the two sets. But we cannot say that this variable will assume a value in the final solution because it's not a basic variable. Okay, so in the final solution, after you apply the Gauss-Jordan method, the variables that will have a value different than 0 are the ones that are represented with this structure, a 1, and the rest of the column is zeros. Anything that is not having this structure in the final solution will have a value of 0. So non-basic variables will be always equal to 0. What a non-basic variable can do is, like, if you if you identify, and I'm not saying that's the case for this, and we will discuss this in a minute. If we have something, let's wait until the next case, and then we'll make more sense. This, I don't want you confused, but this is a non-solution case, okay, no solution. Then the second case is the one that, suppose that you know that case one does not apply. So you don't have a row with zeros and the right-hand side different than 0. So you eliminate that case. Now you move to case number 2. Suppose that case 1 does not apply and the non-basic variables, the set of non-basic variables is empty, which is what we are representing here. Since all the columns have that format of 1, a single one, and the rest of them equal to 0, all of the columns are showing that format, then we know that we have a unique solution, meaning that the solution that we obtain after applying the Gauss-Jordan method, that's the only solution for that linear system of equations. So this is the case in which you have a unique solution. You look at the matrix on the left, you look at the columns, you see the columns are 1s, 0s, 0, 1, 0, 0, 0, 1. All of them share the same format. So all of them are basic variables. So this system has a unique solution, which is what you observe in the example that we discussed on Wednesday last week. So the matrix has a unique solution. The set of basic variables is x1, x2, and x3, while the non-basic variable set is empty. And then we get to the third case, which is where we have multiple solutions for the same system of equations. So suppose case 1 does not apply and non-basics is not empty. So again, you look at the left side of the matrix again, and you observe that these two columns are not 1, zeros, and zeros and 1s. Okay, so you know this is not a case in which you have a unique solution. Also, you observe that even though you have a row with all zeros, the right-hand side of that row is 0 as well. So that row is not telling you that you don't have a solution, because zeros means nothing. Okay, that has no impact on the solution. If you had a number that is different than 0 here on the right-hand side, if you have a number that is different than 0 here, then the problem has no solution. But that's not the case here. All of them are 0. So we look at each column now, and we have 1 zeros, 1 zeros, 1 zeros. These two, the last two columns, are not in the same format. So we identify that AX equals B will have an infinite number of solutions, because we have two sets now. We can identify the set of basic variables and the set of non-basic variables. So this group right here, x1, x2, and x3 are the basic variables, and this group right here are the non-basic variables. So what this means is, in order for you to get another solution for this problem, what this is representing, let's say this way, we will see how that works when we apply the simplex method, is that you found a solution in terms of x1, x2, and x3. That's good, but you can also find a solution in which you have x1, x2, and x4, or you can find a solution in which you have x1, x2, and x5 with different numbers, and you still can solve the system of equations. That's what this is representing. But as this final solution is showing, is you have a solution for x1, x2, and x3. Okay, so you have only a solution in which x1 equals 3, x2 equals 2, and x3 equals 1. Okay, that is one solution for that system, but you can find all the solutions in combinations with x4 and x5 as well. Okay, so it will depend on what the iteration that you perform for your system of linear equations. When we talk about the simplex method, what we typically do if we want to find another solution is we say we're going to enter or we're gonna switch one of the variables from the basics to the non-basics, and one from the non-basics to the basics, and we solve the problem again to find another solution. Okay, so but for now, I just need you to identify the type of solution that we are finding after applying the Gauss-Jordan method. 3 cases: no solution, unique solution, and multiple solutions. Any questions? Yes. Inconsistent? What do you mean by inconsistent?
So if 0 equals 3,
If 0 equals 3, you're talking about the last row?
yeah,
Oh, so if this,
or 3 equals 0.
oh yeah, so basically that's what we are saying, that when that's the case, then that means that the system has no solution. So so what that means is, when you try to find a solution to the system, there's no combination of values that will allow you to make that system of equation happen. Okay, so you.
I guess what I'm saying is, another word for that is inconsistent. So I think it's
So in this case, oh, so if you go back to case 1, let's go back to case 1. This one, yeah. Well, yeah, well, I mean, you can say that it's inconsistent because it's not going to meet the conditions for solving the equations. You can see it that way too. But you have no solution, basically. There's not going to be a combination of values that will give you, like if we go back to this system of equations like this. Here we have 2 equations, very simple equations. So what that solution is telling you is you are not going to find a value for x1 and x2 that will make this equal to 5 and this equal to 0. That's what that solution is telling you. Okay, you will not find an x1 equal to something and x2 equals to something that will meet those 2 equations in which you have x1 plus x2 equals 5, 2x1 minus x2 equals 0. If you plug in any combination of numbers there, there's no going to be a combination in which those 2 equations will be feasible or satisfied. Obviously, that's not the case for this example, but I'm trying to show you what that means. Good questions, good discussion. So again, the 3 cases, we can summarize this with the following flow chart. So how do you know what type of solution you have? This is a summary of the Gauss-Jordan method. The end result of the Gauss-Jordan method will be either case 1, case 2, or case 3. So you start by looking at the no solution case. If you see that you don't have, if you have something like zeros and a number on the right-hand side, that means that you have no solution and you're done. So that's this side of the flow chart. So if that's the case, then no solution, you're done. If that's not the case, then you have to find the basics and the non-basics. If you find that the non-basics are empty, then you have a unique solution. If you find that the non-basics are not empty, then you have an infinite number of solutions, which is this case. Okay, questions? So how do you identify the basic variables? How do you identify that? How do you know that you have a basic variable based on the matrix? How do you know? Yes, so you have column with a single one, and then the rest of them are zeros. If you have a column that is not meeting that condition, then that is a non-basic variable. Okay, so if you get to that case, then you know that if your non-basic is not empty, meaning that you have a couple of non-basic variable at the end, then you have multiple solutions. Okay, good. So we got to this problem, a very simple problem. And this is what I want you to work on as your lab for today. I want you to work on this by yourself on a page. I mean, if you don't have paper, I have paper with me. So you write down your name. You don't have to write the whole thing. Just write the equations and solve the problem using the Gauss-Jordan method.
So you're gonna submit the paper, right?
You get the paper, you keep the paper, and then what I'm going to ask you is for you to take a picture and upload it to Canvas by the end of the day. Yes. So I'm going to give you, I don't know, 5 to 8 minutes to work on this. And then we are going to discuss the problem in class. So if you are at home, you should be able to access the lab also in the modules. So if you go to modules, you will see the, I mean, you can see it on the screen, the problem, so you can work on it in a piece of paper. And if you go to the modules, you will see the same problem listed as a lab. So to submit, you just go to that lab link and you upload your picture of the solution. And what I want you to tell me also at the end of the solution is if you have a unique solution, no solution, or an infinite number of solutions. And in your solution, please state clearly this has no solution, this has a unique solution, or it has multiple solutions. And remember the trick, if you're done, you can check if your solution is correct based on what we talked last time. You can input the values that you obtain into the equations. And then if you see that after solving the equations, you get the same value on the left and the right, then the solution that you obtain is correct. The other way to do it would be to multiply the augmented matrix by the solution vector and then check if the right-hand side, the original right-hand side equals the scalar product. It's the same thing. So I see that some of you are done already. Let's give another 2 minutes. We can discuss the problem. The next time, if we have a lab and you're in class and you want to use the board to solve the lab, you can do that too. We have a lot of boards here, so, and markers. So at the end, you can just take a picture and submit that as well. Okay, who needs more time? Let's start then. So here we have the augmented matrix. This is based on the system of equations. So we have 1, 1, 0, 2 for the first equation, minus 1, 2 for the second equation equals 3, and 1, 1 equals 3 for the third equations. Okay, so if you look at that first column, you already have that in the format that you needed. So you don't have to work that column. You have a 1, 0, 0. So we can move to the next column and work with that one. So again, the process that I'm going to follow might not be the same that the one you follow, but at the end, we should get the same solution in terms of x1, x2, and x3. So that doesn't mean that your solution is wrong. If you follow a process and you get the same solution in terms of x1, x2, and x3, then your solution is correct. So I didn't do elementary row operation 3 in this one. So I went straight to work with the order of rows that we have originally. So what I did was I multiplied this by minus 1. And I got the following matrix: 1, 1, 0, 2, 0, 1, minus 2, minus 3, 0, 1, 1, 3. Okay, so I understand that you can just do a flip, flip 2 rows and then get that one and avoid that step. But again, at the end, what is important is that you get the same solution. So now we get the positive one in the middle, and we have to work on the making the first row for column 2 equal to 0. So that's what we're going to do next. So I'm going to multiply this row by -1, and then I'm going to add that to row 1. And again, you don't have to write all this process of I'm multiplying -1 plus row 1, and I'm doing that for the purpose of the lecture. You can just proceed as you were solving the problem, and that's fine. So the new matrix is 1, 0, 2, 5. So that's the new row after multiplying row 2 by -1 and adding to row 1. And the rest of the matrix should be the same. 0, 1, -2, -3, 0, 1, 1, 3. Any questions this step? No, good. So we will proceed with the same. Now we want to make that third row for column 2 equal to 0. So I'm going to multiply that by -1, that second row by -1, and add that to row 3. So multiply this by -1 and add it to row 3. You get the following matrix: 1, 0, 2, 5, 0, 1, -2. Those two stay the same. And the new row is 0, 0. You multiply this by -1. That's +2. And then you add it to 1. That's 3. And then -1 times -3 is +3 plus 3. That is 6. Okay, so that's the column 2, the process to get column 2. Now we move to the third column. In order to make 3 equal to 1, I'm going to multiply this by 1/3. So the new matrix will look like this. First two columns are not going to change. 5, 0, 1, -2, -3. Then we have 0, 0, 1, and 2. And we proceed to make the rest of that column equal to 0. So we start with the second row. So I'm going to multiply this times 2. I'm going to add that to row 2. So the first row stays the same. And then we get 0, 1, 0, 1, and 0, 0, 1, 2. We get one more step. So we multiply by -2, this one, and then add that to row 1. So at the end, we get what we were looking for, the identity matrix. 1, 0, 1, 0, 0, 1, 2. So my solution for this problem, again, this is x1, x2, and x3. My solution for this problem is x1 equals 1, x2 equals 1, and x3 equals 2, which is what? What type of solution? It's a unique solution, correct. So make sure that you state that in your solution. This is a unique solution. questions. If you did it following a different order of elementary row operations, you should be able to get the same solution. If not, check your solution because we have a unique solution for this problem. Questions? We're good? Okay, so let's talk about some other concepts for matrices and vectors, and then on Wednesday we will start with the material for the class. So again, we are doing this review, but what we want to get to is into solving engineering problems using operation research. But we need this background in order to get to that point. So let's talk about linear independence and linear dependence. So if we have a set of vectors, in this case, there are a set of row vectors all having the same dimension. So they have the same size. A linear combination of the vectors in this set B is any vector of the form C1, which is a coefficient, times B1 plus C2 times B2 up to CK times, should be BK here, where C1, C2 up to CK are any scalar. So these are values, positive or negative values. So for example, we have a set V here with two vectors, 1, 2, 2, 1. So if we compute this form, basically we're subtracting these two vectors. So we multiply by 2 the first one and then subtract the second vector. We obtain a new vector 0, 3. We proceed with the same two vectors and we apply the other combination, B1 plus 3 times B2. We obtain a new vector 7, 5. Okay, so we have a set of vectors. We have a linear combination of vectors. In this case, this is the linear combination 0, 3, and this is another linear combination because we have different scalars. So in this case, the scalars are 2 minus 1. In this case, the scalars are 1, positive 3. So a set of vectors is called linearly independent if the only linear combination of vectors in this set B, the only linear combination, like the one that we did here, the only one of vectors in V that equals 0 is the trivial linear combination in which you have to make every single C equal to 0. Okay? If the only linear combination in which V equals 0 is when you make them all the C equal to 0. If you find any other scalar that satisfy this condition, then those vectors are linearly dependent. So a set of vectors is called linearly dependent if there's a non-trivial linear combination of vectors in V that add up to 0. So for example, show that V, this set of two vectors, is linearly dependent set of vectors. So how do we show that? I have those notes. Okay, so since two times 1, 2 minus 1 times the other vector 2, 4 gives you 0, 0. And this again, based on by just looking at the numbers, I can come up with these two scalars. And I can find that set of scalars, C value 1, C value 2, 2 and minus 1, in which I can create a vector 0, 0. So there's a non-trivial linear combination with Z1 equals 2 and C2 equals -1, that yields 0. Then, or thus, V is a linearly dependent set of vectors. Okay, so by finding that combination of scalars, in this case, C1 equals 2, C2 equals -1, we can find that linear combination that gives us 0. So that means that these vectors are dependent. If we find no trivial combination, and the only way that we can make them equal to 0 is by making Z1 and C2 equals to 0. That means that the vectors are linearly independent. Questions? Okay. So what does it mean for a set of vectors to be linearly dependent? If a set of vectors in V are linearly dependent, the vectors in V are in some way not all different vectors. So the direction specified by any vector in V cannot be expressed by adding together multiples of the other vectors in V. So for example, in 2 dimensions, 2 linearly dependent vectors lie on the same line. So you can see that in the first graph on your left, those are 2 vectors that are linearly dependent. They have the same direction. On the right-hand side, or figure number 2, you have 2 linearly independent vectors. They have different directions. Okay, so in terms of the graphical representation of this concept, that is the meaning. The direction is the same for dependent vectors. Direction is different for linearly independent. Makes sense, right? Linearly independent and dependent. The rank of a matrix, another important concept. So we have A representing a matrix, be any m by n matrix, and denote the rows of A, this set A, by R1, R2, up to Rn. So in this case, we have a set, this matrix A that we are using for our system, and we have these many rows. So in this case, we have m rows. M could be any number. Let's say 5 rows. M equals 5. So the rank of A is the number of vectors in the largest independent subset of these R, which is the set of rows in this matrix A. So how do we find the rank of a matrix? We apply the Gauss-Jordan method to matrix A, the original matrix, and we let A prime be the final result. So after you apply the Gauss-Jordan method, you're making basically your matrix an identity matrix. It can be shown that the rank of A prime equals the rank of A. The rank of A prime equals the number of non-zero rows in A prime. Therefore, the rank of A equals the rank of A prime, which is the number of non-zero rows in A prime, which is equal to the number of non-zero rows in A. So in order for us to find the rank, we have to apply the Gauss-Jordan method and then find out how many non-zero rows we have in that matrix, resulting matrix. So for example, we have this matrix A. Looks like the identity matrix, but we have switched these two. So it's no an identity matrix. And we want to find out the rank of this matrix. So after applying the Gauss-Jordan method, so essentially what we are doing is we are multiplying this row by -1 and adding it to row 3. And also multiplying this row by -1 and also adding that to row 3. We obtain this new matrix A prime after applying the Gauss-Jordan method. So you can see this new matrix A prime has a row 3 that is equal to 0, 0, 0. Okay, so if we were going to count the number of non-zero rows, in this case, we have only 2. Because in this row, we have a 1, and in this row, we have a 1. The rest of the rows have zeros. Okay, so the number of non-zero rows in this case equals 2. So we now have that number. So how do we use that information? Set of vectors V equals B1, B2 up to Bm is linearly dependent if the rank of A is less than the number of rows of the original matrix A. So if we go back here, the original matrix has 3 rows. The number of non-zero rows is 2. So if the rank of A is less than M, then we say that that set of vectors B1 up to Bm is linearly dependent. We go back to the example. I mean, you can intuitively, based on that information, know that these set of vectors are linearly dependent because we know that the rank is 2 now after solving the Gauss-Jordan method. So that's the conclusion that we are going to make. Again, M equals the number of rows. Of the original matrix. So we have M equals 3 in this case. We found the number of non-zero rows after applying the Gauss-Jordan method. Equal 2. So we are going to make that conclusion now. So find out if the set of vectors is linearly independent given this matrix, which is the same that we just solved. So we know based on the solution that the rank of matrix A prime equals 2 because the number of non-zero rows equals 2. So the rank of A prime equals 2. And we know that this is less than 3, which is the number of rows of the original matrix. Okay, so using this equation, we compare those values, and then the set of vectors in B are linearly dependent because the rank of A prime, which equals 2, is less than the number of rows of the original matrix. Okay, so in this case, we have M equals 3 for A. After solving the Gauss-Jordan method, we find the rank of the matrix, which is the number of non-zero rows for A prime. That's 2. We compare those numbers. We found out that the rank of A is 2, is less than the number of rows 3. So that means that that set of vectors, B1, B2, and B3, are linearly dependent. Questions? Let's talk about the inverse of a matrix. So the inverse is also a very important concept for this class, because if you find the inverse, then you can solve a set of linear equations very easily. Okay, so let's talk about the inverse. A square matrix is any matrix that has an equal number of rows and columns. The diagonal elements of a square matrix are those elements Aij such that I equals j always. So in order to make that diagonal, so this is 1, 1, I equals 1, j equals 1, I equals 2, j equals 2, I equals 3, j equals 3. So that is what this is meaning. Diagonal elements, you always have I equals j. So a square matrix for which all diagonal elements are equal to 1 and all non-diagonal elements are equal to 0 is called the identity matrix. So this is an example of an identity matrix. And we name the identity matrix with an I and with the number of rows. So M is the number of rows. So in this case, we name that identity matrix I3. I for identity, 3 for the number of rows. So we have the identity matrix. For any given M by M matrix A, the M by M matrix B is the inverse of A if, when you multiply that matrix B by matrix A, you get the identity matrix. Okay, so that's what the inverse is. You multiply the original matrix by this new matrix B, and you obtain the identity matrix, then that means that you have the inverse. Some square matrices does not have inverse. If there's does exist a M by M matrix B that satisfies this BA equals AB, which is equal to the identity matrix, then we write that B is equal to A to the power of -1, which represents the inverse. Okay, so here I have an example. Just want to illustrate this point. So you have A giving you this matrix B, which is the inverse. So when you multiply these two matrices, you get the identity matrix. So let's do that. If you go to this process, or if you input that into your calculator, you will see that the multiplication of those two matrices equals the identity, which is the point that I'm going to illustrate. So if you find that matrix B that gives you this solution, the identity matrix, then B is the inverse for your original matrix A. Okay, so why are we interested in the inverse? Why? Suppose that we are interested in the inverse. Why are we interested in the inverse of matrix? Suppose that we want to solve a linear system AX equals B. Go back to our lecture on Wednesday, in which we showed that if we have a set of equations, we can represent them as in a matrix form, with a matrix A, a vector X, and a vector B. So that's the form that I'm showing, AX equals B. So A is the matrix with all the coefficients, X is the vector of decision variables, and B is the vector of the right-hand side. So we have M equations in M unknown, right? So this is a square matrix. Suppose that A inverse exists. The results of multiplying both sides of the equation by A -1, or the inverse, equals the following. So we start with the original equations, or the linear equations, AX equals B. If we multiply both sides by the inverse, we're multiplying here A inverse by A, and on the right-hand side, we're multiplying A inverse by vector B, right? The right-hand side. If we go to that process, we know that on this side, we're gonna get the identity matrix. We showed that already. And if we multiply this side, we get the inverse times B. So the identity matrix by X equals the inverse of A times B. So what does that mean? That means that if we get the inverse of the matrix, of the original matrix, we can obtain the solution for the system right away. If you get the inverse, the only thing you have to do to solve the system of equations is to multiply that inverse by B, and you'll get the solution for your system of equations. So that's why it's very important, the inverse. If you can get the inverse of that matrix A, in order to solve that system of equations, you get the inverse, you're done. Because the only thing you have to do is multiply that inverse by B, and you get the solution for your system. So this will make more sense when we get into the operation research material, in which we find a solution for a problem. Let's say we are planning for a production schedule, and then we change some of the coefficients on the right-hand side. Let's say we say, okay, instead of the demand being 200 units for next week, what will happen if we make the demand 500? So I changed the right-hand side. I changed B, the vector B. I want to find a solution. I don't have to solve the whole thing. I have the inverse. I can multiply that by B and I can get the new solution for X. Okay, so that's the purpose. Good. So this shows that knowing A inverse enables us to find the unique solution to a square linear of a system of equations. The Gauss-Jordan method may be used to find the inverse of a matrix or show that that inverse does not exist. So using the Gauss-Jordan method, this is how we get the inverse. Given matrix A, create the augmented matrix A. So okay, this is A. So for you to find the inverse, create the augmented matrix A slash inverse. So you're putting the inverse on the right-hand side here. And what you're going to do is you're going to solve the Gauss, or you're going to use the Gauss-Jordan method to make this side of the matrix equals to the identity matrix. Once you find the identity matrix on this side, the resulting matrix here, because you're going to be performing the operations for all of them, the resulting matrix on this side is your inverse. So by applying the Gauss-Jordan method to this side, you're creating the inverse on this side. So transform A into the identity matrix using the elementary row operations. So on the next steps, that's what we are doing. We're making this the identity matrix. And as we transform this into the identity matrix, that left-hand side of the equation of the matrix, we are also transforming this side. So going through the process, you find the last step, step number 4. You can see that on this side of the matrix, we get the identity matrix. So I'm using my pen to mark that identity matrix. And then this side of the matrix is your inverse. So you transform this into the identity matrix. And by doing that, you got the inverse. Okay, so that's how you obtain the inverse. Some matrices do not have inverse. So for example, consider matrix A applying the Gauss-Jordan method yields A prime. So in this case, we end up with a zeros in one of the rows. So matrix A does not have a solution since the bottom of row of A prime has zeros. This can only happen if the rank of A is less than the number of rows. So if M by M matrix A has a rank that is less than M, then the inverse does not exist. So going back to what we learned about linear dependence, linearly independence, and the rank of a matrix. So if that case in which you have a rank that is less than the number of rows, that means that the inverse does not exist. Okay. What else we have? Okay, so let's go through this, and then I'm going to stop after this slide. So use matrix inverse to solve linear systems of equations. So as I mentioned, if you know the inverse, you can solve the problem. So we have two equations here, 2x1 plus 5x2, x1 plus 3x2 equals 4. So, and we know the inverse, okay, that inverse is given. So what do? We can find the augmented matrix here, right? But if we know the inverse, as I mentioned already, we can solve this problem really fast. The only thing you have to do is to make x equals to the inverse times the right-hand side. So in this case, the inverse is 3 minus 5 minus 1 and 2. And we are multiplying this by vector b, which is 7 and 4. So we end up with, after performing that multiplication, x1 equals 1, x2 equals 1, which is a unique solution for your system. So instead of trying to solve this using the Gauss-Jordan method, if I have the inverse already, I can multiply that matrix and that vector, and I can get the solution. Questions? Yes, so what you do is the scalar product. So you have 3 times 7 plus minus 5 times 4. And that would be the first. And then you have minus 1 times 7 plus 3 times 7, 5. Yeah, and I have minus 1 times 7 plus 2 times 4. So that will give you 1, 1. Any other question? Good. So I'm going to stop here. We're going to continue on Wednesday, and make sure that you upload your solution by tonight so you can get the credit for lab 1. There's no questions, then I'll see you on Wednesday. Yes.
So, first we're gonna start lecture 2 or
We're going to start lecture 2. I'm going to complete this one, and then we're going to start lecture 2.
you upload lecture 2
Beforehand? Yes, yes, I will do that. So you can print the slides. Yes, yes, I can do that, definitely. Any other question? Good. So I'll see you on Wednesday.